Today I'm going to cover AP Precalculus topic 313 about trigonometry and the polar coordinate system. So you can already see right off the bat we've got something a little interesting here. This is what the polar plane looks like. We're going to be mapping just your regular Cartesian rectangular plane to polar, but let's talk about what we're looking at here. So the polar coordinate system is a coordinate system based on angles and distances. So rather than going to the right or to the left for the x and then up and down, we're going to find an angle and we're going to go out a certain distance. Okay, the pole is what we call the origin of the polar plane. So it's the same location as our normal origin. It's going to be right in the center, but we call it a pole. And then rather having an x-axis and a y-axis, we simply have just one polar axis. And it is what we think of as our positive x-axis. So everything's going to be measured off of just this one line. So the coordinates. You have known and loved our Cartesian coordinates, x and y. In polar, rather than having an x and a y, we're going to have an r and a theta. The r, or really the absolute value of r, is going to be the distance from the pole. It's absolute value because r can be negative, and we'll see how to handle that here shortly. Our other variable, or other coordinate, is theta. And that's going to be the angle from the polar axis. So starting at the polar axis, we'll go some angle away from that. Now, just like when we're dealing with our unit circle and those types of angles, if our theta is positive, we measure going counterclockwise from the polar axis. And if our theta is negative, we measure our angles going clockwise from the polar axis. All right, so let's look at some coordinates on our polar coordinate system here. So you can already see I have my r and my theta. Our thetas are going to be in radians, and they can be positive, 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 negative, negative, positive, or negative, negative. So we're going to look at how this plays out in graphing. It's really straightforward. We're going to go 3 pi over 6. So kind of two options, and this is going to be pi over 6, this is going to be pi over 4, this is going to be pi over 3. These first two aren't our unit circle values. We're more comfortable with these ones. So 3 pi over 6, we're going to go two ways to think about this. Either go out 3, 1, 2, 3, and around to pi over 6, or what I think is a little bit easier is to find pi over 6 and then move out 3. This is going to be sort of our practice, so I want you to try to plot for 7 pi over 4. So we'll find 7 pi over 4, which is down here, and we're going to go out 4 units. 1, 2, 3, 4. All right, so our next coordinate is 2, negative 4 pi over 3. So positive 4 pi over 3 is that much. So we're now kind of more thinking about magnitudes. So here I'm going to go that same amount, which is going to end me here, but we're going clockwise instead. And then I'm going to go up 2 units on that axis. So your challenge is 2, negative pi over 2. Negative pi over 2 is going to be clockwise pi over 2 units, which would be down here, and then we're 2 units on that axis. All right, a negative, negative. Again, I'm going to show you two ways to think about this. Sorry, a negative, positive. So first, my preferred method is to go to the angle, which is a counterclockwise pi over 4. But rather than going 5 this direction, we go through the pole to the other side. Alternatively, you can kind of treat this like a number line and go -5, 1, 2, 3, 4, 5, and then proceed going counterclockwise pi over 4 units. Okay, so next we have -3, 4 pi over 3. So if I go find 4 pi over 3, that's down here, and then I'm going to go through to the other side of the pole to the 3. Last is a negative. So again, two different methods. My preferred is to find -7 pi over 6. So positive 7 pi over 6 is down here. So negative pi over 6 is this line here. And then I'm going to go through the pole to the other side. Or go back to -4 and then go clockwise 7 pi over 6 to get to that value. So -3, negative pi over 6. Negative pi over 6 is going to be right here, and we're going to go through to 3. So that's how we plot coordinates in the coordinate plane. Now notice that in our regular Cartesian coordinate system, rectangular coordinate system, positive was always here, negative, negative, and so on. Here, no such thing occurs. So like this last one was a negative, but it was in the second quadrant. And let's point to this last one. This we plotted as -3, negative pi over 6, but I could call that 5 pi over 6, or 3, 5 pi over 6, and that would be that same point. So unlike in the Cartesian coordinate system, we have an infinite number of ways that we can refer to a single point, not only with combinations of positives and negatives, but I could add 2 pi to this and end up at that same location. So let's dive into that a little bit. So our next task is we're going to find 3 other coordinates that represent the given coordinate with a restriction that our theta needs to be between -2 pi and 2 pi. And part of that's, we could just take this, add 2 pi again, add 2 pi again. There's 3 other coordinates. But we're going to be a little bit more thoughtful. So to do this, we have a positive, so I'm going to find my 3 other coordinates as a combination of a positive, negative, a negative, positive, and then a negative, negative. It's helpful to have an idea of where our point is, so I'm going to go ahead and plot our first point at 2 pi over 3. Okay, so my first alternative coordinate form is positive, negative, which means my r must be positive 2. That distance isn't going to change. But rather than going to this point going counterclockwise, I'm going to go all the way along this long way, which is going to be equivalent to 5 pi over 3. Okay, now one thing, that'll be a -5 pi over 3. So just thinking about this, I went this direction pi over 3, we went this direction 5 pi over 3. So if I add pi over 3 and 5 pi over 3, we get, if I add a distance of 5 pi over 3 and a distance of pi over 3, that gives me 6 pi over 3, which is 2 pi in a full circle. So that's one way to kind of check. A negative, positive. So here, this is one I kind of reverse what I said before. I like to kind of think about treating this as a number line and going back 2, because this has to be a -2, and then figuring what angle I need to do going counterclockwise to arrive here. So this is going to be pi, that's going to be 4 pi over 3. And then last, again, we're going to have a negative. So I'm going to start here and go clockwise to that angle, which is going to be a -2 pi over 3. And again, if I add those absolute values, we'd get 6 pi over 3 or 2 pi. All right, let's do another one. Okay, first, I'm going to start by graphing. So here's 5 pi over 6 out 1, 2, 3. Okay, our positive, negative. We're going to have a 2. To get to this same going clockwise, that's going to be a 7 pi over 6. We have a -2, so I'm going to start at, these are 3s. 3. If I go -3, and then I want to get to the same thing going counterclockwise, we get a long journey here, which is going to be 11 pi over 6. And then our next one, -3, not drawn as ugly as the other ones, but this time I'm going to start here and go clockwise to that point, which is just going to be pi over 3. Our last one, 4, 7 pi over 4. Okay, 1, 2, 3, there's 4, 7 pi over 4. Okay, so we're going to go clockwise is pi over 4. We'll have a -4, so I'm going to start here and go counterclockwise, which is going to be 3 pi over 4. Okay, the other thing to think about is if I want a -r, what's opposite this is 3 pi over 4, and then my -r would get me there, if that makes more sense for you. So -4 clockwise is going to be 5 pi over 4. So that's how we can find different coordinates. Although the coordinate system looks a whole lot different because my grid isn't going vertically and horizontally, it's this kind of dartboard looking thing, we really are plotting points that on the same plane. It's just how we're arriving at those points is a different process. So our next part here is going to be going between the rectangular polar system that you have dealt with forever, x, y, so this coordinate here would be x, y, and converting it between going from polar to rectangular, rectangular to polar. So on this same diagram, okay, in polar, we go out a certain distance r at some angle theta. So we can relate all of these things, so this point is also r theta, but we can relate all of these things using our basic right triangle information, meaning right triangle trig and the good old Pythagorean theorem. So I'm going to write a couple of statements of equality, and then we're going to use those to convert between the red x and y Cartesian or rectangular coordinates and the blue polar coordinate system. All right, so thank your geometry teacher because they have set you up for success to convert between polar and rectangular coordinates. So first we're going to look at, well, let's look at what I set up here. So there's just a lot of relationships here, and there's more than what I wrote, but these are the ones that we're going to use to develop these conversion formulas. So first, cosine, adjacent over hypotenuse would be x over r, and I've color coordinated everything. Sine of theta is opposite over hypotenuse, or y over r. Pythagorean theorem, x squared plus y squared equals r squared. And tangent of theta is going to be y over x. So for our first conversion, we're going to, given an r and a theta, come up with an x and a y. So I'm going to come up with an equation for x in terms of r and theta, and an equation for y in terms of r and theta. And that's going to come from these first two, because I can simply multiply over an r to get r cosine theta, and I can multiply over an r here to get an r sine theta. Now, if you've been paying attention, these are not actually new formulas. We used these way back in topic 3.3 when we were coming up with the coordinates of a value on a unit circle based on a distance and an angle. So same idea. But x equals r cosine theta, y equals r sine theta. The nice thing is this is easy to remember because on your unit circle, cosine is x, sine is y, and we're just going out a certain distance r. Okay, so given our coordinates, our polar coordinates, we're going to turn them into rectangular coordinates. So I always like to write my formulas first because we have to have memorized anyway, and that's a helpful tool. So my x coordinate for this one is going to be 12 cosine pi over 6. And you can do all of this like in a parentheses coordinate setup. But I'm just doing it separately. Okay, and then we're going to evaluate using our unit circle, using our knowledge. Our x value at pi over 6 is root 3 over 2. My y value at pi over 6 is 1/2. So if I simplify this, we get 6 root 3. Here I just get 6. So the coordinates here are 6 root 3 and 6. Now let's think about this just graphically. If I were to plot something like 12 pi over 6, well, that's going to be over out 12, about here. Well, if I went 6 root 3 up 6, we're going to get to the same spot. So this is the polar version of that coordinate. This is the rectangular version of that coordinate. Okay, next, I've already got our formulas here, but we just dump them in. So 2 cosine 3 pi over 4, 2 sine 3 pi over 4. Cosine 3 pi over 4 are negative root 2 over 2. The y value there is a positive root 2 over 2. So these simplify to a negative root 2 here, a positive root 2 here. And we get the coordinates, negative root 2, root 2. And it should all make sense if I were to graph this. We're in the second quadrant. Our x and y's are going to be the same. So it all matches. It should all feel good and connected. Next, we're going to go the other direction, and we're going to start with our rectangular coordinates and go to polar. I brought back our diagram here. For these, we're going to use these two. So with this, we want to start with an x and a y and end up with an r and a theta. Well, r, real simple. I can solve this Pythagorean theorem here by taking the square root. So I'm going to take the square root of x squared plus y squared. And because of this, when we generate them, we're just going to get a positive r. And we know that there's an infinite number going from rectangular to polar, so there's more than one option, but picking a positive r is probably the safe bet. For theta, I can isolate theta using tangent inverse. So these are our formulas for going from rectangular to polar. Now we have a little bit of an issue with the second piece of that, with the tangent inverse. So I'm going to talk about two different cases, and I'm going to talk about case one is, fortunately, we get a tangent inverse that's on the unit circle. If that's the case, just pick the right one. Okay, so what I mean by that is choose the theta in the correct quadrant. So let's look at some examples. So negative 2, 2. If I were to plot that, we're right here in the second quadrant. So let's look at our formulas. R is easy. R doesn't matter. We're going to have the square root of negative 2 squared plus 2 squared, which is going to be 4 plus 4, or the square root of 8, which can simplify to 2 root 2. Do you need to simplify? Don't know, but I would expect this would be on a multiple choice, so I would be comfortable recognizing either as the correct value here. Theta is going to be the tangent inverse of y over x. So we're looking for the tangent inverse of negative 1. On our unit circle, there are two locations where this happens. When our x and y coordinates are the same but opposite, in the second quadrant at 3 pi over 4, and in the fourth quadrant at 7 pi over 4. Okay, both of those are solutions to this. Both of those are not a solution to where this one's located. We want the one in the second quadrant. Okay, so then we're going to put this together as a coordinate. So my solution here is 2 root 2, 3 pi over 4. Okay, let's do another one. Now I'm going to cheat a little bit here because it is x squared plus y squared, but if I square it, it's going to be positive. So even though this is negative, I'm just going to do 4 squared plus 4 root 3 squared, which is going to be 16 plus 16 times 3. 16 times 3 is 48, plus 16 is 64, which I would absolutely simplify that one because that's just 8. Theta is going to be the tangent inverse of our y. Negatives matter here, so we're not going to drop them in this step. So we get tangent inverse. Now here, negative divided by negative is positive. We know tangent is root 3 in both the first quadrant and the third quadrant when both the x and y values are negative. The steeper slope is going to be down at 4 pi over 3. So my coordinate here is 8, 4 pi over 3. For this last one, you can try to use the formulas and you'll sort of arrive at a correct solution. But how I'm going to handle this one is by simply graphing and thinking about putting it on a polar plane. So 0, negative 3 is going to be straight down. Okay, if we make this into our polar plane and we've got circles and we've got lines, my r, the distance out, is going to be 3, which if you put this in the Pythagorean theorem, you're going to get 3. My theta is going to be 3 pi over 2. Now, we haven't been given any restrictions, so I could say like negative pi over 2 if you wanted. You could even make a negative r and a positive theta if you're feeling like it. But just if it's on one of the quadrantals, one of our axes, I would just plot it and use our brains there. The other case is if we do the tangent inverse and it's not a unit circle value, which forces us to have to use our calculator. The issue being, if we're using our calculator has the inverse tangent function, which means it's going to give us values, output values, between negative pi over 2 and pi over 2, which is just fine if we end up in, if our angle, or a point, is in the first quadrant or the fourth quadrant. And we're fine with a negative angle. We've already talked about that. But all day long, you're only going to get values in the first and fourth quadrant. You're not going to get a second quadrant angle or a third quadrant angle, even if that's where your coordinate is. The good news is we know that the period of tangent is pi, so we can take whatever our calculator gives us, which will be in either the first or fourth quadrant, and add pi to that to get to our second or corresponding third quadrant angle. So let's look at that here. Our r is going to be the square root of 4 squared plus 3 squared, which we all know 3, 4, 5 triangles there. Our theta is going to be the tangent inverse of 3 over negative 4. So if we do this, we're going to get a value of negative 0.64. So pi is about 3-ish. So negative pi over 2 is negative 1.5-ish. So this is somewhere in between there in the fourth quadrant. But this is in the second quadrant, negative positive. So what we're going to do is add pi to that value. So that will be my radian equivalent, 2.49. That's a little bit less than pi. So that's our theta. We're going to be accurate to 3 decimals. So my coordinate here would be 5 and a radian value of 2.498. All right, so now we're going to go a whole different direction, sort of, but not really, and talk about the complex plane and the polar form of complex numbers. So as a reminder, a complex number is a number in the form a plus bi. A is our real part, b is our imaginary part. Well, we can graph complex numbers on the complex plane, where this is our real axis and this is our imaginary axis. And then we treat it just like a coordinate, where 2 plus 3i is going to behave like the coordinate 2, 3. But this is our real and this is our imaginary. So it's 2, 3. This would be 2 plus 3i. This is going to behave like the coordinate negative 3, negative 1. This is going to be like the coordinate 0, 2. So we're going up 2 on the imaginary axis. And then this would be the same as 3, 0. Okay, so what we can do is turn these complex numbers into their polar form. The math is going to be identical for the most part to what we've been doing. It's just the structure is going to look a little bit different. So if I have a complex number and we have the corresponding coordinate x, y, we're going to call this x plus yi. From our previous conversions, we know x is equal to r cosine theta and y is equal to r sine theta. So we're going to write this as r cosine theta plus I r sine theta. Okay, so it's going to look kind of different, but it's just the polar form of a complex number. The conversions are going to be just the same. So if I have an x and a y and I want an r and a theta, r is still going to be the square root of x squared plus y squared. My theta is still going to be tangent inverse of y over x in our correct quadrant. It's just when we write the number, it's going to have sines and cosines in it. So we're going to convert these complex numbers to their polar form. It may be easier for you to think about this as the coordinate negative 8, 8 to find the r and the theta. That's our x and our y. So my r, just like with rectangular to polar normal coordinates, is going to be the square root of 8 squared plus 8 squared, which is root 128, 64, and 64. So that would be 8 root 2. Theta is tangent inverse of 8 over negative 8. Tangent inverse of negative 1. Okay, whether we're looking here or here, that's in the second quadrant. So we're looking at 3 pi over 4. Now, rather than writing this as a coordinate, we're going to be using that whole structure that I just showed you. So it's going to be in parentheses 8 root 2 cosine 3 pi over 4, close parentheses, plus I 8 root 2 sine 3 pi over 4. So it looks quite different. There's things that we can do with this. We're not going to get into that in AP Pre-Calc, but things like multiplication, quotients, powers are actually a whole lot easier with the polar form. But right now we're just converting. Here, before we kind of talked about this, I'm going to go just to our graph. So my negative 6 is going to be on the real axis, back 6. So my r there is going to be 6. My theta is going to be pi. So when I write this one, this is going to be 6 cosine pi plus I 6 sine pi. Again, why would you take a nice pretty number like negative 6 and turn it into this? These are equivalent. There's just some other things that we can do with that. All right, and here's the good news. Going from polar form to rectangular form, super easy. I'm not even doing a formula. Just simplify. Okay, so I've got our fun-looking complex numbers that are written in their polar form. So to convert, we're just going to do this calculation. It feels kind of awkward that this is what it looks like, but that's the structure of the polar form. But we can simplify. This is going to be 1/2 the cosine of 5 pi over 6. Our x value there is negative root 3 over 2. The y value is 1/2. So if I simplify this, I get negative root 3 over 4 plus 1/4 I as the rectangular form of the complex number that's written in polar form. Do one more here. Cosine, our x value root 3 over, sorry, not root 3, 3 pi over 4 is root 2 over 2. My sine value is positive root 2 over 2. So we get a negative 2 root 2 plus 2 root 2 I. So this was pre-calculus topic 313, all about polar coordinates.